Cool. So, lab 2 is due Friday. Lab 3 is due next Friday. Is lab 2 going okay? People are, yeah, it's a little steep. Lab 3 is also pretty challenging. I am open to extending lab 3 by an additional week, if that would be helpful. But at the moment, let's keep it due next Friday. Try to keep working at it. Kind of the purpose of this class is basically everything that you could possibly want to know about system Verilog design is in this class. So it's if we take out a lab or if we take something out, it just means that now you have not practiced that skill. Now it's just one fewer things that you can put on your resume. I think honestly, yeah. So I inherited this class from Dustin Richmond. I think he did a really great job making all of the assignments. And I don't really want to remove things, but also I know that they also. I was looking at them. They're much harder than the assignments that I would usually make personally. But I think that they're really good. So so please keep working at it. I guarantee by the end of this class, your brains are going to be twice as big. Yeah, huge. And your resumes will also be huge.
Can we add labs to resume?
So again?
Can we add labs on resume?
You would say skills. You'd be oh yeah, I have experience in Ready Valid, AXI, this FPGA type, this FPGA type. Now you have experience with the Xilinx standard cells and the Icebreaker standard cells already. You now are gaining experience with Coco TV and test benches, and we'll be doing more test bench stuff later on. So that's what you would write in your resumes. You would write all the individual skills. Yeah, Ella.
Is there any chance we get tutors for this class?
So there's no tutors. However, there are there are two unofficial tutors. That's what I'm trying to say.
Mitchell and Zion.
Mitchell and Zion. You can ask them any questions, although they are not guaranteed to know the answers to everything because they are doing this out of the kindness of their heart and they're not getting paid. Yeah, but you're welcome to ask them any questions. Yeah, Albert.
The second assignment for, I think it was for one of the modules, we have to add, one of the test benches is looking for parameters that you're not, using.
Oh, thank you. Yes, small, yeah. Sorry, you said lab 2, right?
I think it's lab 2. Count. Yeah, count.
So I
put it in Piazza, but I don't know.
After you ran the command, I think I left out one parameter that I forgot about. Yeah, okay. I still need to respond to that.
But it fixes it. You just put the parameter, just don't use it.
Yeah. Sorry. I'll respond to that shortly. There is a fix for that. I just haven't gotten around to respond. Yeah. Okay. Any final questions? Yeah, Presto?
Can you go for debouncing again?
Debouncing? Yes, I can. I'll go over that after I go over what I want to go over right now. Leroy.
To fix the missing parameter names, I didn't run your script. I just copy and pasted the correct parameter names into the file.
Is that probably fine? Yeah.
Okay.
So I'll tell you why we are getting parameter issues. The reason for that is because Dustin, who I inherited the class from, prefers a coding style from the University of Washington called, what is it? Now I don't remember what it's called. I think it's the Bespoke Silicon Group coding style or something. And it's very popular, but it is not as popular as the low-risk coding style for Verilog. I prefer the low-risk coding style of Verilog, which came out of Cambridge and Zurich. So it's more of the European coding style, but it's much more popular because Europe is bigger in the open source hardware world. So I am switching over his coding style into the low-risk coding style, and occasionally I accidentally miss a couple variable names in the tests. I thought I checked everything, but I obviously did not. So you will probably continue to see a couple bugs. It's not a big deal if you just use the base jump or the Bespoke Silicon Group coding style parameter names instead. You can just, any sort of hack that you find to fix it is totally fine.
Is there a wiki for what to do for each style?
I think the Bespoke Silicon Group style is in the Canvas. I'll put them in the lab notes for today. But yeah.
Thank you. Sorry about that.
Yeah, another question, Marco?
Yeah, you were saying that open source stuff is more popular in Europe. Is this just
That's
due
true.
to funding or like what's
Why is it? Yes, I would say partially is funding. I would say mainly because the U.S. has become quite monopolistic due to like NVIDIA, Intel, like ARM. These like huge corporations are extremely proprietary and secretive about all of their hardware. In Europe, it's a little bit more collaborative because they are all punching up, like they're all punching up to Intel, and like we have all the big companies, and none of the big companies are very like free with their information. Intel does a little bit of open source FPGA stuff. NVIDIA has released like some of their GPU driver is open source, but for the most part, kind of funny. I actually had a job interview at Intel like a few years ago, and I like mentioned, I'm like, oh yeah, like I have tons of experience in Verilog. I'm like, oh yeah, I have experience in Icarus and Verilator. And my interviewer said, oh, what are those? Which is hilarious because if you Google like Verilog simulator, those are the two first things that come up on Google because they're the things most downloaded. And like even the people like at Intel have no idea what's happening in the open source community. So, anyways, yeah, but
So they have like their own?
Say it again?
They have like their own version of anything?
Absolutely, yeah, exactly. So there are commercial tools that are better than Verilator and Icarus, but they can cost $100,000 a year or something. So we are using the free versions that do not cost that much. If you want access to those tools, you can just join like a research lab. Research labs like Dustin's lab has access to these expensive tools, but this class does not. Yeah, Albert.
Are these tools like the compilation, or like are the languages different too? Or
The language is standardized. It's an IEEE specification, but the tools are, there are several companies that have a slight different implementation of the tools.
so like synopsis and like those things?
Exactly, yeah. So there's a Synopsys like simulator and a Synopsys synthesizer, and a Synopsys place and route tool. And then there's a Cadence synthesizer and a simulator, synthesizer, place and route. And then there's Siemens as well, and like Xilinx. Yeah, all of these companies individually have implemented their own tools. And again, which is kind of weird because like, we're all familiar with like Clang++ and G++ and Python and like Java runtime environment. Like all of these, we're used to like as engineers, as like software engineers, we're used to these tools being free. It's like, oh, like if you can program the language, then you should be able to just like test if your code is right. But in hardware, because there's a few orders of magnitude fewer people actually writing hardware, there are fewer people that are working on open source competitors. When you have, when you just have like millions of people all writing C++, then you're going to have really good open source tools because everyone's using the open source tools. When you only have a couple thousand people writing Verilog, then the tools are not going to be, as good. Yeah.
Isn't it better for like most compilers to be open source because then it's like easier to find issues and stuff like that? So like how do the commercial ones kind of keep up, if that makes sense? 'Cause
Yeah. I mean, probably a good thing, or a big reason why they keep up is because they're some of the most valuable companies in the world. It's like you think, like, what are the top companies? It's like, like Apple, NVIDIA, and it's like basically just all the chip companies. And so, yes, they're all reinventing the wheel, but they are all trillion-dollar companies that can afford to reinvent the wheel. That's kind of the reason. Yes, absolutely. If there was one open source like suite that did everything, then probably the world would be better. And that's kind of what Verilator and Icarus are attempting to be. They're just developing a little bit slower than the other tools. Maybe in like 20 years, all of the commercial tools will be, no longer relevant. Interesting. Okay, I'm going to stop talking about Verilog for a bit. I want to now talk about memories. Okay, so First we're gonna do a quick little rehash on ready valid. So ready valid is the parallel interface that we discussed on Monday. The idea with ready valid is if you have two things that want to communicate with one another, so let's call this, producer and consumer. So the way ready valid works is the producer will produce data, and when this is in this, this is a wire. This wire is always connected no matter what, regardless of if the data is like valid or not. But we need some sort of flag to determine whether this data is actually like valid. Like maybe we're in the middle of producing a product, or maybe we're in the middle of doing a division. And so while we're working, we don't want this data to be like advertised as valid data. So instead, what we'll do is we will have a whole nother wire that will be valid. It will be called valid. And this will denote whether our data is valid. But let's say the consumer maybe is also in the middle of doing something and it is not yet ready to receive this valid data. Like, maybe the consumer and producer are both like working, and then the producer finishes working and then it tries sending out valid data. Well, the consumer needs to send back a flag that says ready if the consumer is ready to actually receive this data. And notice I'm actually, let me do this. So I will shrink this down. So you can see that there's a valid output coming out of the producer and a ready input going into the producer. But on this side, the net names would be called ready out and valid in. There we go. And so the idea is that if the producer wants to send out valid data, but the consumer is not yet ready, then the producer will stall until the consumer is ready, and then vice versa. If the consumer is ready to receive data, but the producer has not sent out data, then the consumer will stall. And only when you have the case where both valid and ready are high at the same time, then the producer and the consumer will both recognize that both of them are ready and valid, and therefore data flow will occur. So only if, I'll say if and only if valid and ready data is sent. Cool. Good. Excellent. And kind of the purpose, the purposes of ready valid is, I would say, to initiate state machines. Because maybe you are in a state and you don't know exactly when to switch over to the next state, or maybe you're in an idle state and you're waiting for inputs. When you receive ready and valid, then you will know, okay, it's time to switch over to the working state and to read in the incoming data. So that is kind of the purpose of ready valid, is to initiate the next state in your state machines. Good. So ready valid, super popular, used in absolutely everything. And issue with that though, right, is, well, if the consumer is not yet ready to receive anything, or if the producer is not sending out valid stuff, well, the issue is now we have to stall anytime, we don't have ready and valid. So what would be nice actually is if we could find some way to kind of add some sort of buffer right here. Because what could be nice is maybe if the consumer is maybe not yet ready, well, maybe what we could do is we could just put whatever valid data is happening over here, maybe we could just put it inside of a temporary buffer for a second. And then now the producer is able to put that in the buffer, and then the producer can go back to working. So now the producer is not going to be stalled, even if the consumer is not yet ready. And so then maybe while the producer is working on the second bit of data, then maybe the consumer now becomes ready. And so now instead of pulling out of the producer, now it can pull out of this buffer. And then now the consumer again grabs the data from the buffer and then will no longer become ready. So it's now working on this. And so having this buffer right here now means that these two, like producer and consumer, they no longer need to wait on each other. Make sense? Okay. Further questions? Question? Yeah.
So like once the producer is done and if the consumer is not ready, it's just like okay,
Yeah.
like writing to memory or like some sort of buffer. And then how does the consumer know like that it's in the buffer?
Right. So what will happen is there will actually be a ready valid interface on this. So this will be generating, like this will have a valid, yeah, let's do this. So the buffer will have, oops. The buffer will duplicate the ready valid signals. So these pink names right here, these are the names generated by the buffer. So you can see like if the producer is sending data to the buffer, then it will be sent in through valid I, and it also needs to check like is the buffer ready to receive this this data, and then if it's ready and the producer is valid, it'll send it into this buffer. And at this point, now the valid output will be set high because now there is something in the buffer. Okay, good. Well, nothing's stopping us from actually making this as big as we want. Like maybe we could have like 10 things right here. Maybe we could just keep adding things into this until finally maybe it fills up, and then after the 10th thing, then then we can stall the producer. But most likely, like if we put like 10 things in, like that's going to take a long time for it to stall, and by that time the consumer has probably like grabbed all of them out. So maybe we're not going to stall. So adding like buffers right here, this will improve the speed and like the throughput of data, because now the producer and consumer don't need to wait on each other. Instead, now there can be this buffer in the middle that can like kind of coordinate the data flow. And often this buffer is implemented as something called a FIFO, first in, first out. People heard of this? Okay, good. FIFOs. So now the question is how do you actually implement a FIFO in Verilog? So FIFOs actually one of the most popular things in Verilog designs. Like oftentimes you will see dozens, if not like hundreds, of FIFOs all throughout a chip. Like no matter what chip it is, if you're a CPU, GPU, any sort of thing where you're passing data from one ready valid interface to another ready valid interface, almost all the time you're going to have a FIFO in the middle. And this FIFO can have anywhere from, I don't know, 1 element in it to like 10 elements, potentially like 1,000 elements in it. FIFO is extremely popular. Okay, now let's think about how to implement this. Any questions before we switch over to Verilog? Okay, good, cool.
Actually, quick question.
Yeah.
So I guess just to confirm, like the consumer doesn't consume the data until ready O and valid O are both one, right?
Ready I and valid O are both one.
Ready I and valid O. Okay.
Yep.
And basically ready I is like the consumer is ready to receive the data.
Yes.
And valid O is like the producer has produced valid data.
Valid O is does the buffer currently have something in it?
Okay.
Yeah. And ready I is the consumer ready to receive something from the buffer? Oh.
How, like if the consumer says they're ready without the producer producing any values, what does the buffer do?
The buffer won't do anything. It's like if the buffer is empty then the valid signal is going to be low.
Okay.
Yeah. The second the buffer gets something, then valid will go high.
And then do our like buffers like ever like overflow or like something like that? How does the producer know that the buffer is not full?
Yeah, so if the buffer ever becomes full, actually, okay, question to all of you. If the buffer becomes full, then what signal here will become 0?
Ready. Ready out.
Ready out, yeah, exactly, that's ready out. If the buffer is full, then the buffer is not ready to receive more data. Yeah. Okay, cool. So let's go and implement this buffer. And this is another case where I probably should have done this ahead of time, but I ran out of time, so this will be exciting. Okay, also this is, is it gonna work? Oh, it's not gonna work. Wait a second. Okay, cool. So this actually comes like straight out of, I think, homework 3, I think lab 3. So you can basically just copy exactly what I'm doing today and then use it for lab 3. So, okay, yeah. So here we can see clock reset, then also data in, and then data out. So in theory, there should be like something between here. Like this is where the buffer should exist, right here. Okay. Think about it for a little bit first. Let's assume that data entries is just 1, and let's store it in a flip-flop for now. So don't worry about like arrays. We'll do it with an array and with like more elements later. But for now, let's just consider that we just want one single like element in our buffer. Okay, think about how to do this, and yeah, brainstorm ideas for the next 1 minute. Feel free to chat with people around you. Then we will go and implement it together.
You misspelled entries.
And
Entires.
and wait, and trees. Thank you. Okay, so I'll do the first part for you. So you should probably make a flip-flop like this. So we have data D, data Q, and then now data Q is driven by data D, and then always FF block. Okay. So now we probably need to assign data D. So we can put this maybe in always COM. Maybe this is overkill, but so maybe by default, let's just make data D, data Q. Okay. So what here? Albert.
Oh, this is like with syntax. When you do like the always complex snippet,
Yeah.
what's the point of like the colon block name?
Oh, sure. So this like name here.
Yeah.
To be honest, I actually don't know the purpose of this. I think it's for like simulation reasons. If you do something like, I'm not running a simulator on this, but if I was running like, yeah, CocoaDB, like Icarus or Paralator, I could do something like info. And if I did info, then it would tell me like what line of code I'm on, and it would also tell me what module I'm in. and it would tell me the name of whatever always column I'm in. I think this is the main reason.
Okay,
Um,
thank you.
yeah, I'm not sure if there's really another reason.
Do we need to write begin and end for it once?
For if else? No, but I just always like to, you don't have to. No. The reason you need to is if the if statement is longer than just one line. Like if our if statement becomes 2 lines, then you definitely need begin and end.
Oh,
Yeah, Gustav?
Would one module have multiple always com blocks, or would we just involve combination logic inside of a block?
Yeah, you can absolutely have more than one always comb. When you create an always comb, though, there should only be one like variable assignment localized to one always comb block. So like here, this always comb block is assigning data D, and we could also make it assign like data out or something. But we could not make a second always comb block that also assigns data D.
Okay, so it's like a sign statement that you can't multi-drive.
Exactly, yeah. Exactly, yeah. So you can't multi-drive, and the way you multi-drive would be having like a second always comb that drives that same net. Yeah, Albert.
Okay, are we allowed to use registry files for implementation or not?
Say it again?
Like
Oh.
Reg files, like the stuff you share with 700, like the image?
We're gonna get there. I think we'll get there. Yeah, I think things will be more clear. Okay, good. So, remove this. So here's data I. So maybe we can say something like if, I don't know, we can say if ready out and valid I guess. Then that, sorry, not that, already data I. Something like that. Well, I guess now we need to assign ready out though. So, okay, maybe we need to keep track of like another flip-flop that tells us whether we actually have something, like whether we're storing something. So maybe we can call this like valid D, valid Q. So this is going to like say like if we are currently storing a valid bit of data, then this should be 1, otherwise it's 0. So okay, let's go and test this out, and I will go and quickly just do this. So valid. Okay. Anything else that we should put in the always column? So what should valid be by default? Maybe just Q. It's probably fine. Like we can just grab whatever the previous value was. And then what happens if we now take in data? What happens to valid D? What should valid D become on the next?
True.
Yeah, I think it should become true if we just took in data. Okay. Now, question for you. How do we know whether we are... hold on. Okay, yeah, so we can probably assign this valid O, just straight to valid... hold on, sorry. I'm going to move these up. That's good. Moving these up, I'll assign valid out. So I'll do equal to valid Q. Okay. But now we need to assign probably ready out. So the question is, when are we ready to receive more data?
If we're not full.
Yeah, exactly, if we're not full, okay? And we are full when we have something that we are currently storing. So when ready out, I guess when, I don't know. We can say like when we are not storing something. That's what I'm thinking. Okay. Does it make sense? Am I missing anything? It's very possible I'm missing something. Yeah.
In a buffer that's got like multiple spots, we might be valid and ready. How would we handle that?
Sure. We'll get there when we get there.
Sounds good.
Yeah.
I'll
So
take that.
cool. Okay. I will now. Okay. Let's just check. Hopefully this works.
Did you ever use Ready Eye?
Yeah, that's
ready I. Oh, thank you. Okay.
And you guys said,
So now we can do something like if, if valid out, ready I. Okay, so what happens, if we are currently valid and something is ready to take in this valid data, then what do we do?
Nothing. You wait.
Yeah, I guess because we're already
Oh
driving.
wait, something else is ready. We send it.
Well,
We already have the data there, right?
So the data actually, is already there.
But if it was like a multiple cube, then we would have to figure out how to shift it out.
Well, so this only has one bit of data. I'm going to say that we probably should go and wipe that like element. We should
Oh,
probably
yeah.
say like we are no longer storing something now. So on the next cycle, we will no longer store something because it has just taken it out because it was ready to take it, so it did take it. So cool. Okay. Hopefully that is good. Let's see. Click optimize. See what happens. I may have forgotten something, but that's fine. Okay. Data I was not used. Let's see. What? Why? What? Data I? Data O? Okay, something weird is happening.
I don't valid.
Where's
I don't
data?
think we ever use data.
Yeah, we
Oh.
never data
Oh,
assign
thank you. Perfect. Assign. Yeah, data O. Oh, let's go and actually put it in here. Thank you about that. Okay, great. So data O is equal
Why
to,
Indy always come?
I don't know, just for fun. So let's say by default, data O is unknown. Like we don't care what this value is, but when, actually, no, I take it back. We'll say assign data O. Yeah, we'll just say this. It's equal to data Q. It's fine. If we want, we could do like a cool simulation thing where we say if we are valid, then set it to data Q. If we are not valid, then just set it to all X's.
Wait, this is only possible in simulation?
Well, in simulation, in synthesis, when you have an X as one of your inputs to a mux, so here's a mux, and when X is your input, what will happen is this will just be optimized away into just this. But in simulation, this will tell us a little bit more information.
Oh,
Yeah. Okay, let's go and test this. I'll optimize. Hopefully this works. Okay, good. So it seems to be working a little bit better now. I'm going to go and reset this. Okay, and now if I don't know, do the data 52. Okay, so I've sent the data 52. Now I need to say that this data is valid. Okay, so good. So now we can see it is valid over here. If I go and now try to send another bit of data, so if I say 53, you can see like data O, even if I send data is valid now, it's still storing 53 because it is not yet ready to receive this new value of 53. But now if I go and say like, okay, yes, I am ready, then now we should see it should change to 53. There we go, now it's 53. So cool, we have successfully made our little buffer here.
Sorry, could you explain like that workflow again? Like,
Yeah.
how did you like update like to 53?
Yeah, so what, here, let's do, so if I do 50, and then say, hey, I'm ready, or this data is valid,
Mm-hmm.
then now it updates, the output updates to 50, and we can see the data is valid.
we can use them.
But doesn't ready O have to be valid, or ready O have to be high as well?
It was high, but now it's not because it's currently storing data. So if I go and
that's high.
reset, you
Okay.
should see that ready out goes high. So it
Right.
is now ready to receive data. And now if I go, so you can see it's still ready, still ready, still ready. Now if I send valid data, now it's no longer ready because it's full.
Oh, okay.
Okay, good. Here's our one element buffer. And yeah, well, it's not a very good FIFO because it can only take in one element. So I guess, yeah, now the question is, how do we implement this as like an actual actual FIFO, like not just a single element.
Does Verilog support multi-dimensional arrays,
It does.
but not in a useful way, presumably?
I don't know how that will fix the problem, but
Okay.
because multi-dimensional arrays are basically just really long single-dimensional arrays that are just
okay.
indexed slightly
That's
differently.
what I thought.
Yeah, Albert, yeah.
Okay, so
Probably you make a register file with whatever amount of indexes it's specified.
So, okay, we're not going to use register files. So, okay, the way that FIFOs usually work is they use memories. Specifically, they most often will use SRAMs. And an SRAM, usually kind of what the interface for them are, and this goes for most memories, is you have a read address fed in, and then out of the read address, you get read data. So you can think of this as like an array. So if you have like an array of integers and you feed in an address into that array, or like an index into that array, then you get back data. And most of the time, this reading will be synchronous and will happen one cycle delayed. So when you put in an address, on the next cycle, you will get back the data. That is usually how memories work. And I will say that this is an SRAM. Okay, so actually right now, this is considered a ROM, a read-only memory, because we are only reading and we're not writing. If we instead want to have this be like a read and write memory, then we could now go and add a write address and a write data, and then a write enable. And so now we can write to this memory and we can read from it. And this also usually will happen with a one cycle delay. And SRAMs are extremely efficient area-wise. They're usually very small. Like the amount of transistors that you can pack into a transistor is like, it's going to be the densest possible when making SRAMs. Like SRAMs, if you look at an SRAM like implemented on a chip, it looks like just a big like block. Actually, let me see if I can pull something up. So let's see if I do.
Are CPU registers SRAM typically, or is it something else?
I think it depends, but I think often yes.
Okay.
So this is the Intel 12900K CPU. It was their top of the line CPU from like 2021 or something. And if you are interested in where the SRAMs are, it's basically anywhere that looks just like a big kind of block. So like this is a big SRAM right here, like a big SRAMs. Like you can see SRAMs. You can see this right here, it looks a little more random. This is logic, this is not SRAM. But like this looks more structured, so this is SRAM. You can even have like kind of small little blocks of SRAM like within. So maybe like this little section right here, this looks like it's SRAM. Yeah, so SRAM is all over the chip. Actually, I think SRAM accounts for about 70% of all like chip area. So by far, like the most common produced probably engineering thing ever is probably like SRAM cells. Like it's not like, I don't know, nails or screws. It's probably like SRAM cells. Yeah, yeah.
I see those are repeating blocks. Are those like each a separate core?
That's exactly right, yeah. So you can see here are like the power cores. So it looks like there's 8 power cores. And then here are, I guess, 8 efficiency cores, I think, right here. Yeah, so you can see the efficiency cores are much smaller. Yeah, exactly. Yeah, Albert.
How do you make like a SRAM? Is it like a flip-flop or like what is it made of?
Sure, yeah, I can mention that. So SRAMs, so if you were to look at a single bit of an SRAM, this is what it would look like. So it would be two inverters just pointing into each other. It would, wait, what am I doing? Sorry, is this right? Hold on. I am, what's going on? Sorry. Thank you, yeah, okay. So it is, like this. Okay, so question for you. Assume that this value is 0, okay? If it's passed through this inverter, then what is the value here?
1.
1, okay. If this is 1, passes through this inverter, what is the value here?
0.
0, okay. So this is considered like a stable state. Well, if I now go and duplicate this and do something different, so now let's say there's a 1 over here, then what is the voltage right here?
0.
This is 0, yeah. And then similar, if I go and pass it through here, then now what is the voltage right here?
1.
Is 1. So you can see, depending on like what state this circuit is in, that is what stores a 1 or a 0. Now, these transistors that make up this inverter are designed to be really weak and really small, to the point where if you go and attach another transistor right here, maybe this transistor is really big, it's really conductive, maybe what you can do is just attach like a bit right here. Maybe you can say like, oh, like drive this with a voltage of 1. So now this, like when we turn on this transistor, then even though this is being charged to 0 by this inverter, this like transistor is so big that it will end up overriding whatever is inside of this.
Yeah, that's how you program it.
So that's how you program it, yeah. So this transistor right here will allow you to like reprogram the internal state. Yeah.
How does it like drain? Because it's like 1 volt, and like you're trying to feed in 0 volts. Like what? How does that work?
So
Would you just have like a grounded portion and you just open?
I'm not understanding. So I guess
Like if you're trying to feed
like the inverter is powered with like, here's like logic high, logic low. This inverter is logic low, logic high. Yeah. So I guess what would happen is when you want to discharge, or sorry, I guess when you want to charge up this 0, what would happen is this 1 would flow in and, well, I don't know. Doesn't, I guess I'm not understanding your question. Yeah,
if it's like already it's saving 1, right? How do we like make it save 0 instead?
Oh, how do we, oh God, I see. Okay, so let's do the same thing, but over here. Then if we wanted to overwrite this and make this 0, then we would go and write in a 0 like this. And now what would happen is, since this is logic 1, just all of this charge would then just go and discharge, like, whatever, yeah, the output of this inverter, it would be all eaten up by this 0, and eventually it would just like fall down to 0.
Wait, would you be able to do that with a single transistor on the side, or would you need 2?
You actually would do it with 2 transistors,
Or
but you could.
Per side, I mean on the left side, can you do it with just 1?
So you can do it with just 1, but yes. So actually, SRAM cells are usually symmetric, and you will have another transistor doing the opposite thing on the other side.
But the single transistor is enough to do each side.
Yeah, a single transistor is enough. This, adding 2 just speeds it up. Yeah.
So I think I missed something. What were the arrows coming out of the inverters in the first one?
This is like VDD and VSS.
Oh, yeah, I see.
Is it all?
Yeah, I'm gonna remove them. Yeah. These are inverters. Okay, good enough. Yeah, you know what? Okay, I'll mention. I wonder if I can find the schematic of SRAM really quick. There's a really good diagram that I like, but I don't have it handy. That's okay. We'll talk more about SRAM on Friday. I'll talk more about the actual structure of it, but this is probably good enough. But okay, but if we now have this SRAM cell, like, okay, like imagine, this is the single bits. Maybe imagine that we could have thousands of these bits, maybe even millions of these bits. It's like a big array, or maybe we could like index into this array and like write certain bits and bytes and whatnot. So if this is our interface though, to where we can like read out certain bits and then we can also write certain bits. And then when we read, then this is the read data. The question now is, how do we utilize this in a FIFO? So let's say maybe this SRAM has a width equal to maybe 8 and has a num entries equal to 16.
Oh,
Question then, so if our num entries is equal to 16, then what will be the width of our read address?
4.
2.
4. Yeah, because there are 16 possible values that a bit width of 4 could have, like 0 through 16. And that, 0 through 15, same with write address. Okay, what would the width of write data be?
The data set.
Yeah, which is what? Which is 8. Okay, what about the read data width?
8.
Yeah, also 8. Okay, yeah, it's the same. Okay, what about the write enable?
1.
Yeah, this is just a flag. It's just, are we currently writing? Good, okay.
Would we use the enable as like our valid kind of ready valid?
Probably something like that, yeah. So what's great is Verilog actually supports memories, like kind of like built in. And most like synthesis tools can properly infer when you are trying to make a memory. So let's go and make a memory right now in Verilog. Come on, thanks. Okay, and I'm going to do it in a different file, so we'll call it mem.sv.
It's similar to like a LUT, right? Like
Yeah, kind of. So we'll call this mem. Good. And so we will have our read logic, input logic. We have our read address, and this will be, what will the width of read address be?
C log 2 of num entries.
Yeah, exactly. It'll be C log 2 of num entries. And let's imagine num entries is 16, so this will be C log 2 num entries. So this is the read address. This is an input. And then we have now write address. Let's also put the read data. Oops. Okay. -1, 0. This should be -1, 0. So. Okay. So that is the read port. If I'm messing anything up. So.
You're missing clock also.
Hmm?
I think you need clock.
That is true.
3s.
And generally, memories don't have a reset because you can't really reset like every single cell inside of an SRAM. And sometimes you can, but usually not. Okay, and then so entries -1, 0. Right. Data. Now we have. Enable. Okay, that should be all of our ports. And now the way that we make memories is actually with an always FF block. Even though it's not a flip-flop, we still use an always FF. So now we do at pause edge, clock, but actually I'll change this to clock for digital JS. And now there's no reset. So now what I will do is say, of course, we need to now make our actual data array. So in Verilog, usually when we want to make a memory, we will do this using something called an unpacked array. Okay, I'm giving you new syntax, potentially new syntax. So first, we will declare just like the width of our data. So we'll just say data width -1 to 0, and then we'll call this mem. Good. But if we now want to make this like an actual array that can store multiple of these mems, then the syntax is open bracket and then just num entries, like this. So this now means that we have num entries levels of like data width elements.
So this is a 2D array.
In a way, it's a 2D array, yeah.
Okay.
Does the function say what you want to see?
It's, I would say this is more like a single dimensional array in C, where each element
Yeah.
is just this big.
I see.
Yeah, like this could be like a uint 8t or something.
So the length is the second number.
Yes,
As
like this
num
is
entries,
yeah.
entries of well obviously yeah.
Yeah.
Now variable name is very helpful.
Sure. Yeah.
Basically, like number of entries among address with like each data with.
Exactly. Yep. Okay, and then if we now want to read out this data, so we can say, so if, actually, what often happens that I left off is sometimes you also have a read enable. So let's just go and add that as well. Sometimes it's not necessary, but I'll just do it. So read enable, I'll say if read enable, then read data is equal to mem at read address. Then I can say if write enable, put this down, then what do we think will happen if write enable?
No, right into address.
So probably mem of what?
Right.
Address.
Also, what time is it?
5:01.
Okay. I wasn't sure if my thing crashed. Sorry, okay, yeah, so write address, write data, right? I think, cool. Good, okay, let's see what happens when we try to synthesize this now. Okay, is this what we were expecting? Maybe. So here is a new type of cell, and this is an array. Sorry, this is a memory. So you can see it has a clock, and on both ports it has a read port, and then it also has this write port here. You can see it's write port because it takes in like the write data, and then here it takes in the read data. So, cool. There we go. Made our first memory. Or potentially maybe you've made one before. So
Can you go back?
second. Yeah. Yeah. Now I'll publish this code.
I do get warnings about bit width mismatches.
I'm not sure why you would get that.
Although
Okay, so if we have this memory now, I guess maybe let's do a quick demo on it. So if I now want to write the value, maybe like 30, maybe at address 30, except I probably can't do that. Say address 3, yeah. So here I'm going to write this data, and I'll also set the data to, I don't know, 3e, yeah. So data is 3e at address 3, and now in order to write it, I need to write enable.
Shouldn't the data fields be data width, not num entries?
Yeah, I'm not sure why.
Did you type out that? R data O and W data I. Should that be data width?
Oh, thank you very much.
Okay, that can also.
Yes. Yep, thank you. Does that make sense? The data should obviously be data width, not num entries. Thank you. Yes, that fixes. I was a little confused about that. Okay, so let's go and test that now. So let's say 3, and we'll write 3e into address 3. So in order to do this, we now need to enable write enable. So okay, in theory we've now written it, but let's now test it. Maybe let's write 4e to address 4 now. So I'll enable write enable. There we go. So now I've written it. Now, if I do address 3 at write address and then do write enable, then we should see, okay, now it says 3e. Fantastic. If I now set this equal to 4, then there we go. Now we see 4. We see 4e. Okay.
It's like it's storing, right? So like if
Yeah.
you go back, it should say 3.
Yeah. If I go back now, then that's 3e. If I go to 4, it's 4e. Yeah. So this is.
Holy shit.
This is cool.
This is like magic.
All right, sure. Yeah, cool. This is how like CPUs will have like huge SRAMs on them. Is basically they just write like a little Verilog array, except instead of num entries equals 16, maybe it'll be like num entries equals like a megabyte or something.
So this right here is SRAM?
This will become SRAM. Yep. I'm abstracting a little bit. There is actually more than just making a simple Verilog array, but let's say for now, this is all you have to do. No. Yeah.
Were the bunches of SRAM on the CPU, were they basically just, is that what the cache was?
This big section, this is the cache.
So the entire thing is the cache?
This whole thing is the cache.
Okay.
Yeah, which is kind of funny. Like the cache takes up like almost like a quarter of the entire chip. Yeah.
Data
And-
is big and logic is small.
Yeah, right. And depending on the chip, you might have more cache versus logic.
3D.
Yeah. Okay, I think we've run out of time. Hopefully this is enough to get you thinking about how to implement like a FIFO now. So you basically just use some sort of module similar to this and maybe add some sort of like counter that's like, I don't know, hopefully we've implemented FIFOs before in like a data structures class. So hopefully you've experienced that. Okay, yeah, any final questions before we leave? Okay, thank you everyone. I will see you on Monday.